Hello there, this is Jude Socrates, and I welcome you to today's video. We continue with our video series concerning infinite series, and today we will begin our study of power series. We will start by defining what is a power series, and we will learn about its interval and its radius of convergence. We will basically be starting part 3 of my textbook, and of course, we will start with section 3, part A. All right, so we will begin our study by motivating it using what we already know, which is the geometric series. So let's recall that we have a fixed real number, and we don't want to be 0 or 1, and we form the series r to the power n, where n goes from 0 to infinity. And we know that this is convergent if the absolute value of r is between 0 and 1. And we also have a formula for the exact sum of this geometric series. So we know that the exact sum of this infinite series is 1 over 1 minus r. We also know that if r is bigger than 1, then the infinite series formed by r to the n is going to diverge to infinity, because r to the n is going to stay bigger than 1. So by the test for divergence, you're automatically divergent. Similarly, if r is less than minus 1, let's say it's negative 2, then we're going to get negative 2, positive 4, negative 8, positive 16. So the terms are not approaching 0 either. So according to the divergence test, our geometric series is going to diverge. All right, so we only said that we're not going to allow r to be 0 because 0 to the n is going to be always 0. Oh, except when we learned about indeterminate forms and L'Hopital's rule, we said 0 to the 0, that's not quite 0, that's not quite 1 either. That's an indeterminate form. But we are going to make an exception for 0, okay? Because if you have r to the power 0, we say that that's equal to 1 if r is not equal to 0, okay? So in order to kind of make our notation easier, in other words, for the sake of convenience, we are going to say that if we have the infinite geometric series 0 to the n, which includes 0 to the power 0, well, we will just forgive that single term and say that that is just equal to 1, because we know that when you spell out r to the n, we say that our 0th term is 1, and then we have r squared, r cubed, and so on. So that first term of 1 is going to survive. Okay, so just for the sake of convenience, we're going to say that 0 to the power 0 in this case will still be equal to 1. All right, so once we release that restriction, we can now say that summation for r n equals 0 to infinity of r to the n will be 1 over 1 minus r, where this is now for all r with absolute value of r less than 1. In other words, for all r between negative 1 and positive 1, which includes the number 0. And does it still work? Well, when r is 0, you're going to get 1 over 1 minus 0, which is still 1. And so this formula is still going to be true. To create a power series, all we do is change the letter. So we're going to do a switcheroo. Instead of the letter r, which appears 4 times in this sentence, we're going to say summation n equals 0 to infinity x to the power n is equal to 1 over 1 minus x for all x between minus 1 and positive 1. Here is our very first, what is called a power series representation. On the left side, this is an infinite series which contains a variable, the variable x. So we will say this is a power series in x, and usually x will be our variable. Sometimes we're going to use the symbol u because we will do, surprise, a u substitution. so that we can have some flexibility as to what we can plug in for you. More on that much later, of course. So on the left side, we have this power series in x. On the right side, well, this is just a function, 1 over 1 minus x. And in fact, we know what this function looks like. We are back in GeoGebra. So we have a function, f of x equals 1 over 1 minus x. Boom, there it is. So yeah, we have, something weird is happening here because we have a vertical asymptote. Okay, so GeoGebra is not perfect. Oh, look at that. There seems to be a line there which disappears when you zoom out because it's not supposed to be there. It's a vertical asymptote. But in our representation, we said that the summation x to the n equals this only if x is between -1 and +1. So really, that function should be defined only between -1 and +1, definitely not including 1. But is there anything wrong with -1? Maybe not. Okay, so if you don't want to see the rest of the function, we can include the domain by typing comma, -1 less than x less than 1. Boom, there you go. So there is still that vertical asymptote, and we can see that the function goes off to infinity as we approach 1 from the left. Okay, now let's think about the power series, summation x to the n from 0 to infinity. We learned about partial sums, right? S0, S1, S2. This time, our partial sums involve x. So guess what? We can graph those partial sums starting with S0. So S0 is simply 1. Now, will this actually give us a graph? No, it gives us a slider. So sorry about that. Let's delete that. How about g of x, g1 of x? Let's call it 0. g0 of x equal to 1. Oh, there you go. And this time, we will restrict x to be between -1 and 1. There you go. So in fact, is there any reason why we can't call it S0? No, there is no reason. Okay, it almost looks like a chemical symbol. S0 of x. Okay, but let's see what happens if we add more terms. So we have S1 of x. The next term is just x. 1 plus x. Oh, we get that line. And again, x is between -1 and +1. Why do I keep using commas? There we go. Okay, so if you studied some basic calculus, and everyone did, yeah, that looks like a tangent line, doesn't it? Okay, let's keep going. Second partial sum, or S2, is 1 plus x squared. Ooh, and again, x is only between -1 and +1. Okay, so there is my S2 of x, and let's see more of this over here. There we go. And we can expand this a little bit. Ooh, blow it up. Okay, and we don't need the part there. All right. So yeah, if you zoom in some more, notice that this is the quadratic S2. It almost looks like it's tangent to our function. All right, so guess what? To save some time, why don't we duplicate input? And this time, we're going to add one more term. Not sure what it's going to label it as. Let's see, will it give it a name? Will it say, oh, of course, new letter, g of x. Okay, so that's because it's automatic. So let's start hiding these older ones. Okay, that was the horizontal line. And now this is the inclined line. Ooh, okay. So if you just focus on our latest partial sum, see how very close those two graphs are. If you're maybe between negative 0.2 and positive 0.2. Shall we go further? Duplicate input. Plus x cubed. One more plus x to the power 4. Of course. So the cubic, that's how a cubic behaves. But now for a fourth degree, it's pointing up in both directions. Okay, but would you agree that this time between maybe negative 0.4 and positive 0.4, you could barely tell those two graphs apart? Okay, so what we can say is that the sequence of partial sums is converging to our function, and we can tell from the graph that not just do they pass through the same point, 0, 1. After all, if you plug in 0 here, you're going to get 1 in all of that. But near 0, 1, those two graphs are almost indistinguishable. And this is one property of power series that's going to be very useful. We are going, spoiler alert, we are going to create power series representations for some very famous, very important functions, namely e to the x, the exponential function, sine of x, cosine of x, tangent of x, yes and no. How about the logarithm? Yep, in a way. So let's go back to our PDF. All right, so we had a very simple power series which just had x to the power n. But in general, we will pick a center, x equals a, and we will form an infinite series which looks like this. Summation n equals k to infinity, c sub n times x minus a to the power n. So in our example, x to the n, well, there's no a. Well, yes, there is 0. X minus 0 to the n is the same as x to the n. So for the geometric series, the center is going to be 0. And to be honest, most of the power series that we're going to look at will be centered at 0. It's the most simple center, after all. We're going to include coefficients beside these powers. So in our case, there are no coefficients. Yes, there is. It's the number 1, which is hiding beside each x to the power n. So we are going to look at power series where you might have something a little bit complicated next to the power. All right, so when we talked about the ratio test, we reviewed the factorial function. You saw it in basic calculus and even pre-calculus. What if we had a power series that looks like summation from 0 to infinity, x to the n over n factorial? Okay, so remember that 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so on. Okay, so this time there is a 1 over n factorial beside the x to the n. So that is our c sub n, 1 over n factorial. Let's think about the ratio test. What is a to the a sub n plus 1? What's the n plus 1th term of this series? So n will become n plus 1, n factorial will become n plus 1 factorial. We've seen this before. So a n plus 1 is x to the n plus 1 over n plus 1 factorial. Divide by this, and remember that it's just the same as multiplying by the reciprocal. Flip that fraction, we get n factorial over x to the n. And remember that n plus 1 factorial is the same as n plus 1 times n factorial, which I scooted over to be under the n factorial. And I scooted x to the n to the left so that it's underneath x to the n plus 1, which we can rewrite easily as x to the n times x. Because now we can see that the x to the n's cancel, x survives, n factorial cancels, so n plus 1 survives in the denominator. Okay, so remember how the ratio test works. We want to take the limit as n approaches infinity of this this quotient. And right now, you're maybe scratching your head a little bit because, wait a minute, there's an x there, okay? And x is usually a variable. And this is where you kind of have to expand your brain a little bit and be a little bit flexible, because this time, even though x is a variable here, when we take the limit, we're making n goes to infinity. Not x, n. So you can think of x as a fixed number, like 5. You get 5 to the power n over here. Or maybe negative 12 to the power n. So if that were just 5, then you will have 5 over n plus 1. As n goes to infinity, that's going to go to 0, isn't it? Okay? Does it matter if it's negative 12? Absolute value of negative 12 over n plus 1, and getting bigger and bigger, still 0. Okay, so x can be a bazillion or negative 20 quadrillion, and as n goes to infinity, that is still going to go to 0. So we can therefore say that that limit as n goes to infinity is always going to be 0. So that tells us by the ratio test that our power series is absolutely convergent for any value of x. Okay, so maybe let's take a pause here, because we started out by saying summation x to the n from 0 to infinity, the geometric series, equals 1 over 1 minus x. Okay, where is the equals here? Shouldn't this be equal to something? Wouldn't that be nice? And yes, that is going to be coming here before we know it. Not in this video though. Gonna have to wait a couple of days. Okay, so what happens if we now move the n factorial from the denominator to the numerator? Now you have n factorial x to the n. So an plus 1 is n plus 1 factorial x to the n plus 1 like before, but this time n plus 1 is together with x to the n plus 1. Divide by n factorial x to the n, our a sub n. Again, the n factorials cancel, and you have n plus 1 surviving in the numerator this time, and a single x surviving also in the numerator. What happens as n goes to infinity? Well, if x is 0, exactly 0, then that's simply going to be 0, so the limit is going to be 0. But if x is not equal to 0, then you can distribute, so to speak, the absolute value into a product, n plus 1 absolute value of x, which is now going to be positive even if x were negative 12. But then that would mean that as n goes to infinity, that will go to infinity bigger than 1, and so therefore our series is going to diverge. And what's left? Yeah, just 0. The only value for x for which the series is going to absolutely converge is when x is 0. When x is 0, 0 factorial is 1, 0 squared, 0 cubed, they're all 0, except when n equals 0. And then you just get 1. So that whole series is just equal to 1. That's kind of boring, don't you think? It only works when x is 0, and when x is 0, you get 1. So yeah, that's not a very useful power series. But yeah, it's still a power series. But yeah, it only converges for one number, x equals 0. And now for something completely different. Here's a power series. We start at n equals 1, going to infinity, alternating minus 1 to the n plus 1. So we start out 2, so positive. 1 over 5 to the n times n to the power 7 over 8. Ooh, p series. X plus 2 to the power n. Okay, so we're going to do some stuff to this. Where is the center? Okay, so how do we find the center? So you look for the x minus a. Okay, is there an x minus a here? Yeah, there's an x. In fact, x only appears once, right there. Okay, so it is x plus 2. but we have to write it as a minus. Well, how can we write plus 2 as a negative something, a minus something? Well, yeah, of course, x minus negative 2. Okay, so therefore, the center of our series is negative 2. Okay, so first things first, identify the center of the power series. Okay, so now let's use the ratio test like we did with x to the n over n factorial to determine what values of x will make the series absolutely convergent and what values of x will make it diverge. Okay, so we want the ratio, that ratio. So our an is this entire thing. And we want an plus 1 over a sub n. All right, so let's copy this whole thing. And we are going to copy this. But do we really need the minus 1 to the n plus 1? No, because we're taking absolute values. So all we need is this, which belongs in the numerator. So that n will become n plus 1. So you know what? Let me copy this. There we go. N becomes n plus 1. That n becomes n plus 1. And that n becomes n plus 1. Okay, we are supposed to divide by this. But of course, instead of wasting our time by dividing by this fraction, we will multiply by the reciprocal. So I'm going to copy this. But since we're multiplying, this goes in the numerator, and this goes in the denominator. There we go. Okay, and we're going to try to simplify this as much as we can so that we can see what that limit is supposed to be. Okay, let's make a copy on the next line. And we do need the absolute value because x is allowed to be negative, or let's say like a negative 4. So negative 4 plus 2, you're going to get negative 2. Okay, so we're going to keep the absolute values. But we are going to put the factors into pairs. Right, so there are 3 kinds of factors. There's a power of 5 right there. There's something to the 7/8 right there. And there's the x, which comes with an n, or an n plus 1. Okay, so there will be 3 kinds of factors. And we're going to separate. There we go. So let's start with the 5 to the n plus 1. Since it's already there, we're going to keep it there. And this 5 to the n, we're going to move over here to join its sibling, the 5 to the n plus 1. Then we have the n plus 1 to the 7/8. Okay, and it comes with, or it goes together with, logically, the n to the power 7/8. Okay, and finally, we have the x plus 2 to the n plus 1, which logically goes together with x plus 2 to the power n. Okay, so I didn't do anything really. I just reorganized the factors, the 6 factors that appear in this long product slash quotient. Okay, so it's now 3 quotients multiplied together. But now I hope you can clearly see how each one of them simplifies. That 5 to the n plus 1 is the same as 5 to the n times 5. So let me put a 5 there, and let me borrow the times symbol here. There we go. Now, what about this quotient? Well, let's do this. Let us wrap the whole thing in parentheses, because there's a power of 7/8 on both the numerator and the denominator. So let's take that power outside, and it becomes n over n plus 1 to the power 7/8. Okay, my apologies, that times is in the exponent. That's where it belongs. All right. And similarly, we'll put the times over here because x plus 2 to the n plus 1 is the same as x plus 2 to the n times another x plus 2. All right, so little by little we are simplifying this, and we can hopefully take the limit very, very soon. So the 5 to the n's will cancel. Goodbye and goodbye. Let's go hop over here. The x plus 2 to the n's cancel, so goodbye and goodbye. And that, sorry, and that kind of looks stupid. So let's just put x plus 2 by itself without a fraction. That looks smarter. Oh, check it out. Now we get to go to infinity. Okay. But as n gets bigger and bigger, we've done this a million times. That's infinity over infinity. We can use L'Hopital's rule. Just divide out by n's. And I hope everyone can see that this limit is simply 1. 1 to the power 7/8, which is still equal to 1. Okay? If you want L'Hopital's rule, that's just going to turn into 1 over 1 plus 0, which is equal to 1. All right, so that limit is simply going to be 1. So we get 1/5 times x to the power 2. We still need the absolute values. So we have the final limit. We can remove this now because that limit is equal to 1. So we have 1/5 absolute value of x plus 2. Okay, so what we've done is the main part, the computational part of the ratio test. We take an plus 1 over an, absolute value, find the limit as n goes to infinity. We get this. So now we have 3 possibilities for the ratio test. So case A, if this limit is smaller than 1, the power series is absolutely convergent. Okay, what else do we know? Well, what do you know? Case B, if that ratio is bigger than 1, the power series is divergent. D, you get a D. So I hope you noticed that, yeah, the really good series are AC, they get a grade of A. Bad series get a grade of D. And yeah, maybe I should stop there. Final case, case C. If that absolute value is equal to 1, what can we conclude? Nothing. The ratio test is inconclusive. Okay? The series might be convergent, might be divergent. We'll find out. So you know what? Let's start there. Okay? Because, yeah, when is the absolute value of this thing equal to 1? Okay, so let's continue. That means the absolute value of x plus 2 must be equal to 5. Move the 1/5 to the other side, it becomes a 5. When is the absolute value of something equal to 5? That something can only be 2 things, either 5 or negative 5. So x plus 2 equals 5, or x plus 2 equals minus 5. So next step, when is x plus 2 equals 5? X equals 3. When is x plus 2 equal to negative 5? X must be negative 7. So for those 2 mysterious values, our series may or may not converge. Okay, let's go back then to A and B. What happens when absolute value of 1/5 x plus 2 is less than 1? We need to solve that inequality. So let me scoot up so that you can see how similar this is going to be to solving an equation involving absolute values. Okay, so we can move the 5 to the other side. It's going to be positive 5, so we don't flip the inequality. So this inequality is equivalent to absolute value of x plus 2 is going to be less than 5. Okay, so instead of equal to 5, it's going to be less than 5, which is equivalent to, so we have solved inequalities like this before. When is the absolute value of a number less than 5? That number should now be between negative 5 and 5. So minus 5 less than x plus 2 and less than positive 5. Which is equivalent to, okay, so now we get to isolate x, subtract 2 from all parts, and we're going to get minus 5 minus 2 is minus 7. Wait a minute, that sounds familiar. Oh, it's right there. Less than x, less than 5 minus 2, which is 3. That also sounds familiar. That's right there. Aha. Okay, so I hope you see a theme hanging around here. We have this final inequality, and that is equivalent to absolute value of x plus 2 greater than 5. Okay, so now this one is a little bit trickier. Okay, so let's slow down a bit. When is the absolute value of a number bigger than 5? So absolute value looks like this. Okay, so 5 is somewhere here. And when is the absolute value bigger than 5? So x should be bigger than 5, or that thing should be bigger than 5, or that thing should be smaller than minus 5. It should be to the right of 5 or to the left of minus 5. Okay? Which is equivalent to, why don't I just copy this? Which is equivalent to x plus 2 greater than 5, or x plus 2 is less than negative 5. You should be to the right of 5 or to the left of minus 5, not in between. Ooh, when did in between happen? This guy over here. All right. So that is equivalent to, which is equivalent to, so x equals 3, or, I'm sorry, x greater than 3, my bad, or x less than negative 7. Okay, so you know what? Let me shrink this a little bit. Let's go to 150. All right, so that we can see the whole picture. Yeah, there we go. The whole picture. First possibility, that ratio that we got is going to be smaller than 1, in which case the series is AC. For this to happen, x has to be between negative 7 and positive 3. Okay, but if the limit is bigger than 1, that is equivalent to x must be bigger than 3 or less than minus 7. But if x is, if the thing, the limit that we found is exactly equal to 1, the ratio test is inconclusive. All right, so at 3 itself and at minus 7 itself, we don't know what is happening to our power series. Okay, so I am going to show you, we're back in GeoGebra because I want to show you what's happening on the number line. Okay, so we said that our series is absolutely convergent between negative 7 and positive 3. So I'm going to click on this and okay, so everything in blue over here, that is good, right? All the values of x that have a value between minus 7 and positive 3 is going to be absolutely convergent. However, if x is bigger than 3 or less than minus 7. If x is bigger than 3 or less than minus 7 in red. Okay, red is bad. Okay, in this case, red is bad. Then our series is going to diverge, right? So there's exactly 1 point here, negative 7, and 1 point here, which is positive 3, where we don't know what's happening to that series when you plug in x equals negative 7 or positive 3. The ratio test is inconclusive. Okay, it fails. By the way, we said that the center of our series, what was it again? Negative 2. Oh, look, it's right there. And 1, 2, 3, 4, 5. Ooh, 5 to the right. 1, 2, 3, 4, 5. 5 to the left. It looks like negative 2 is exactly the center of the interval from negative 7 to positive 3. Okay, so that's going to be very important. What is happening when x is 3 or minus 7? Let us go find out. All right, so that is where we left off over here. Our test is inconclusive when x is 3 or minus 7. But let's go all the way back to the start of the problem. We have this power series. So let's copy it down to the bottom. Okay, so we're going to plug in 3 and negative 7 one at a time. Okay, so we have x is 3 right there. And then later, let me get out of the way, we will plug in negative 7, and we're going to see what happens to our series. Okay, so this is when x equals 3. Oh, wait a minute, 3 plus 2, that's just 5. So that is simply 5 to the n. Okay, oh, wait a minute, there's a 5 to the n down there, so we can cancel those 5 to the n's. Goodbye and goodbye. Okay, so when x is exactly equal to 3, we simply get this alternating p series. Okay, and of course p is 7/8. As long as it's a positive number, we know that alternating p series are all convergent according to the alternating series test. Is it absolutely convergent? No, because when you take the absolute value, you get p is 7/8 smaller than 1, and we know that that kind of p series diverges. But this series converges. And if you want to be specific, yeah, it's only conditionally convergent. But in part 3, we will care about only if the series converges or diverges. Is it good? Is it bad? Okay, wonderful. So when x is 3, we get a convergence series. Okay, so when x is 3, we get this, and the series converges. Okay, when x is minus 7, we get this. And now, what is going to happen? Minus 7 plus 2 is negative 5 to the n. Ooh, before it was positive 5 to the n. Now it's negative 5 to the n. Okay, so be very careful there. Let's put an equal sign there. And instead of canceling right away, we are going to distribute the minus 5 into a minus 1 and a 5. Okay, see what I did there? Minus 5 to the n, think of it as minus 1 times 5. To the n, we get minus 1 to the n and 5 to the n. Okay? So now we can cancel the 5 to the n's. So goodbye to you. Goodbye to you. And, oh, wait a minute. Yuck, we have a minus 1 to the n, but a minus 1 to the n plus 1. So just like this distribute, oh wait, no, I'm sorry, it's a different rule. Minus 1 to the n plus 1, we can distribute as minus 1 to the n times a minus 1. Okay, so minus 1 to the n and another minus 1 to the n, those just cancel each other out because you get minus 1 to the 2n, which is simply 1. Minus 1 squared to the n is plus 1 to the n. Let's spell it out just in case anyone is wondering. That's just 1 to the n, which is equal to 1. So it's 1, and we just simply get negative 1 times 1 to the 1 over 7/8. So it's just minus 1 over n to the 7/8. Okay, we sort of saw that earlier. Oh, except this time it's not alternating. The minus 1 to the n's, or n plus 1's, they annihilated each other out, and the only survivor is a single minus 1. All you do is reverse the sign. And this is a divergent p-series, or the negative of a p-series. Who cares? There's a minus sign. All right, so therefore, thus, the series diverges at x equals minus 7. Okay, so what are our conclusions? When x is 3, the series converges. When x is negative 7, the series diverges. Okay, so thus we can conclude that the series converges when x is between negative 7 but not equal to negative 7 and less than or equal to 3. Okay, it diverges at minus 7, but it converges to 3. Okay, so we can write this in interval notation. And I usually would pause my video so that you won't see what I'm doing, because I'm going to write this with a parenthesis on the left and a square bracket on the right, because we want to exclude negative 7 but include positive 3. Okay, so I'm going to click on something here. Those give me my delimiters, brackets. Okay, so on the left I want an open parenthesis because I don't want to include minus 7. Sorry, minus 7, you diverge. We don't like you. Sorry. But on the right, we will put a square bracket, which is the next symbol over there. Okay, so that is our interval notation. We go from negative 7 to positive 3. Okay, and we give it a name. Okay, so we call this, remember the title, we call this the interval of convergence of our power series. And we give it a name, usually capital I. So capital I equals minus 7 to 3, round at minus 7, and bracket at 3, excluding minus 7, including positive 3. Okay, what else was in the title? Radius of convergence. Okay, so we said that we started with the center. The center is at negative 2. We move to the right by 5, and we get 3. We move to the left by 5, and we get negative 7. Okay, so the center, A equals negative 2, is at a distance of 5 from negative 7 and from 3. Okay, we call, stop that. We call this distance 5. Stop that. The interval of, the radius of convergence for a power series. Okay, and we write capital R for radius of convergence. Our R is capital 5. capital 5, just 5. Now, you remember earlier, though, that we saw this power series x to the n over n factorial, where it's absolutely convergent no matter what value for x you plug into it. On the other hand, if you have n factorial x to the n, the only thing that worked was x to the 0. So that gives us 3 possibilities in general. Whenever you have a power series, there are 3 possibilities, and exactly one of them is going to happen. First possibility, the best kind, no matter what you plug into x, you're going to get an absolutely convergent series. So in this case, we say that the interval of convergence is all real numbers and the radius of convergence is infinite. All right, now the worst kind of series, completely useless. The series will only converge at the center at x equals a. Okay, so x minus a is going to be 0 when x is equal to a. So the only survivor is the first term, which is when n equals k. C sub k times 0 to the k. And remember, we said that 0 to something, we'll just pretend that that's 1. Okay, so we simply get c sub k. But again, completely useless. Don't even go there. The big example that we had, it was convergent from minus 3 to 7. I'm sorry, minus 7 to 3, was it? Yeah, including 3, but not including minus 7. Okay, so this is the behavior in general. There is some real number r, which is called the radius of convergence. In our case, it was the number 5. So that when absolute value of x minus a, our x plus 2, is smaller than 5, we have an AC series. When that absolute value is bigger than r, we got a divergence series. But when it's exactly equal to r, we may or may not have a convergent series. All right, so we got negative 7, positive 3. We didn't know what happens to those 2 numbers because the ratio test is inconclusive. We had to go back to the original series, plug in negative 7 and positive 3 to find out what happened. And what did we get? We got round on the left, square on the right. Okay? But there are always going to be 2 possibilities. The series will not converge on either endpoint, so round parenthesis. It will only converge on the left, but not, it will converge on the left and on the right. So it's square bracket, both on the left and on the right. Only converge on the right, diverge on the left. Only converge on the left, diverge on the right. Okay? So, when the power series actually does converge, then we get a power series whose exact sum will depend on the value of x. And for that reason, it becomes a function of x. We get a power series representation. Now, if only we knew what that function was that made that power series converge, what that power series is equal to. In some cases, we will know what it is. For that one, sorry, I don't even know what it is. I just made it up. All right. So in this case, what happens there, when you look at the partial sums of this power series, their graphs are going to get closer and closer to the graph of this function, f of x. Just like what we saw when we looked at the geometric series. We looked at 1 over 1 minus x. There was a vertical asymptote there. But as we added more and more terms to our partial sum, the graphs of those functions were getting closer and closer to the graph of 1 over 1 minus x. All right, so that is our video for today. Until next time, we're going to see how we can manipulate power series using algebra and calculus. So until then, I hope you enjoy the rest of your day. Bye.